Hey folks, welcome back to another Geometry Nodes tutorial. In this one, we're going to be building some custom bounding box nodes. So this is sort of a continuation of the previous tutorial that we did on packing a collection of objects. And I asked in that one if people were interested in doing rotated packing, and people were interested. So we're going to do that today, but it's a little bit more general. We're going to be making a bounding box for instances, which we will turn into a bounding box for rotated instances. And then we've got a third part where we're going to be basically generalizing our instance bounding box to deal with any kind of group index. And that makes it really powerful because then you can do bounding box calculations within a single geometry, which is great. You can use that in so many things. If you're only interested in a part of this, check the chapters down below. You'll be able to see the part that you're looking for. Otherwise, let's get started. The file that you can see on screen, you have access to this if you want it, if you want to start in the same place. So this has our instance packer, connection info plus node, and the accumulate on curve node. So this is free on Patreon. You don't need to sign up. You can just click the link, grab it. It's the start file. I'll also be supplying the end file in case you just want to grab those final nodes. I'm going to make a slight modification here because this is going along a curve. We don't actually need that for this tutorial. We are only really interested in, well, we can do everything we need with just a straight line. So I'm going to get rid of the Bezier segment, transform and accumulate on curve. I have got it marked as an asset, so I can just remove that. It'll stay in my file in here. And then what I want to do is I want to just grab a points node and a set position node. Whenever you're using an accumulate node, which is what's happening in the instance packer, you have to use the set position rather than the position of your points node. I'm going to go in the y-axis here. Easier way for me to do this actually is with a math node, so vector math, sorry, on the length, multiply by 1 in the y, and that's going to just allow me to create some points like this. Here we go. Now, before I go any further, I do want to just mention that I'm using Blender 3.4 at the moment. The reason is because we're going to be doing stuff with the transfer attribute nodes, which in 3.4 and beyond are going to be the sample index, sample nearest, sample mesh surface, sample UV map is a new one. We're going to be dealing with the sample index and sample nearest in today's session. So we're going to have a set position coming off our length. And if I plug this into our instance on points node, there we go. And I can just get rid of this first align Euler to vector here. And also, don't necessarily need this rotate Euler, but it's good to just demonstrate why we're doing this. If I want to rotate these objects randomly, what I can do is I can plug in a random value in here. And as I start to turn these around, let's just maybe go more in the Z here, you can see that you're getting all of these gaps because the packing is not being recalculated based on the rotated object. So that's kind of the premise for what we're going to be doing here. We're going to be doing our bounding box for rotated instances by rotating the instances and recomputing a bounding box. But it's a little bit more complicated than just make a bounding box. You have to do it sort of analytically. So let's move to the end here. I've got my instances and we're just using these to demonstrate. So whether you have a file like this one or if you've just got a bare file to build as you follow along, it doesn't really matter. All you want is just some instances that you have rotations on, because this allows us to demonstrate why bounding boxes aren't going to work here. All of our bounding boxes have the rotation of the instance, which is a problem because all of the max and min values are just the same as if we didn't have any rotation. And we want to make sure that it's factoring that rotation in because that's what's important to us right now. So let's see what happens if we realize these instances. Let's go ahead, throw that on here. Well, now we've got a different problem. It's fixed up the axis of our bounding box, but now we only have a single bounding box for everything. So what we need to do instead is we need to realize our instances, but we need to calculate bounding boxes per instance still. It's going to be a little bit of data wrangling, so I hope you enjoy this. This is certainly going to be a little bit more of an advanced tutorial. There's going to be some more abstract stuff that we're doing. If you don't know if that's something you want to do, I would recommend the previous one, the collection packing, because that's going to be sort of a good introduction to this sort of passing information around and manipulating the data to do what you need. So first things first, we want to grab our instances and we want to start building up our bounding boxes that we're going to make ourselves rather than using the bounding box node, we're going to be making our instance bounding boxes to happen after the rotation happens. So I've got to realize instances on here, and I'm going to move this forwards a little bit. So what I want to do here is take my realize instances, and we're just going to start off by putting this straight into a group node. Control G. I'm going to rename this one to bounding box instances. And this is going to calculate per instance bounding boxes, which are aligned to the Cartesian, like the world axes. So inside here, right now we just have a realize instances, but we need a bit more information. I need to know where each one of these objects is. Geometry nodes, if we look at our spreadsheet, doesn't really differentiate between objects. We just have a list of, in this case, 33,000 vertices. I need to know which vertices belong to which object. What we're going to be doing first is attribute, capture attribute. We're going to be storing an integer on the instance domain. Remember, we're dealing with instances before the realize. And we're going to be just capturing the index. There we go. So now if I view our viewer here, and you can see everything's coming through black. In 3.4, the viewer doesn't really support the instance domain, but if I plug through from the realize instances instead, then you can see that we have different values. All of these look white just because they're 1 or greater. So I'm going to just demonstrate this just to kind of prove the difference there with a white noise texture. So now you can see each one of these objects, as we would expect, each instance has stored on it a different value. What we're interested in is knowing where the minimum X, Y, Z position is on each of these separately. And it's not a case of finding which point is the most sort of minimum most. It's finding out which point is the least in each of those axes separately. Because if we think about a circle, the point which is the lowest in X and the point which is lowest in Y, these are not the same. If you were just going in this direction, you would end up thinking that this was your lowest most point, and you'd end up with the sort of internal bounding box. We're looking for the least most point in each axis. This is probably sounding a little bit abstract. Let's start breaking this down. Let's have a look at just the position. So input position. Here we go. Now we can see that we have our world position displayed on each of our instances. I'm going to just move this down a little bit in preparation. What I also want to do is try just separating X, Y, Z. So vector, separate X, Y, Z. Now I can see that I have my X coordinates going across here and they're separated. So I should, in theory, be able to find where the least most point and the highest most point of each instance is. Now this would be simple if the statistic node, the attribute statistic node, had a group index. Alas, it does not. We have to do this a little bit more manually, but we can use it to sort of jump off from moving forwards. I'm going to just make sure that I have a 0 to 1 as my maximum sort of gradient across everything. Take your attribute statistic node from the realize instances, set this to vector. We're going to take our position into the attribute. Let's just move these around. I'm going to be taking a map range node, which is under utilities, set this to vector, and we're going to be taking the position and remapping it from the minimum to the maximum values. Now, if I view this one instead, well, now we have a little bit of a more attractive space. We have nothing in the negative. Everything is going to be between 0 and 1. So now if I was to put a separate X, Y, Z on here, you can see that our least most point and our highest most point in each axis is going to be 0 to 1. However, not all of these have 0 to 1 across them. So we need to do something a little bit intelligent to kind of break it apart, transfer things back, do a little bit of like memory management and yeah, data wrangling. I'm not saying memory management like C++, making memory stuff. We're dealing with storing information on sort of sacrificial geometry. So let's see how this is going to work. We have this, which is essentially the core of what we're doing. And we just need to position our geometry in a way that we're going to be able to manipulate it per instance rather than holistically across the whole thing. So if I take my realize instances, and I take a geometry set position. Let's just drop this on here. Now what I can do is I can actually position all of this based on the axis in which we find ourselves. So, for example, I can just position this directly on the X positions. Everything's going to disappear, sort of. I can see a glitch that's probably not coming through. Let's do a mesh to points just for the sake of visualization. So now you can see all of the points exist between 0, 0, 0 and 1, 1, 1, because that's how we've done this. We've set the position to that. So this is great. Everything, however, is overlapping. So we need to do something with our instance index. Let's go ahead and take our instance index from the capture, and I'm going to plug this somewhere over here. So let's put this through a multiply, a vector math multiply, I should say. And we're going to use this actually into the offset of our set position, like this. And maybe I will set my X offset here to be 5. So now what we've got is we have each of the positions from each of the indices aligned on the axis of 0, 0, 0 to 1, 1, 1. And each one is spaced out by 5 meters. This means that I can now do some transferring by nearest and know that when I do my transfer by nearest from here, this point is always going to be closer than this point over here. There's no way for each of these to kind of cross-contaminate. That's not going to happen. We're always only going to be looking now at singular instances. If you haven't done this before, this is probably going to seem a little bit confusing, so just bear with me. We're going to work through it, and hopefully it will start making sense as we go. So I'm going to frame these 4 nodes up here. This is where we're dealing with normalizing our axes. So normalize axes. And then we have our set position, which is going to position these along the points with the offset based on our instance index. We can then start transferring this by nearest to something that can save this information. So each of these goes from 0, 0, 0 at its lowest point to 1, 1, 1 at its highest point in a straight line. What I can do is I can position, therefore, a straight line on each of these positions, 5 meter spacing, in this axis, and as long as I have 2 points on here and I transfer by nearest, the nearest is always going to be the lowest and the highest per axis. It's an odd way of working, requires a bit of mental gymnastics, but it does what we need it to do. So we're going to carry on. Let's create our, I'm going to call it our memory card, our save states. So these are going to be just a bunch of curves, curve lines positioned in the same point in the same direction. Shift A, curve primitive, curve line. We have a start point of 0, 0, 0, an end point of 1, 1, 1. We are going to be instancing on points. This will be the instance. And we just need some points. An easy way for us to do this actually is to take our instances, which I can grab if I get rid of this viewer. So I can see all my instances are here. If I do an instances 2 points, now we've turned all of our instances into points. So one instance becomes 1 point. This is exactly what we need. I can also set my position with this instances to points based on this multiply. Suddenly we have points that exist in the exact same positions as our mesh to point stuff. So what I can do, use these instances to points as our line positions. This gives us all of our base storage. I'm just going to save this actually as storage, just so we know what it is. So it's kind of like our memory. Got my offset in here. And now all we need to do is start transferring the original positions back onto here. So let's go ahead and grab a capture attribute. And we're going to be storing a vector on the point domain. Each of these curves has 2 points. Therefore, we can just store on the 2 points, not the splines, specifically the points. For us to be able to capture, we actually need to realize these instances as well. So let's just drop this like that. There we go. I'm going to call this first capture attribute min, because this is going to be our minimum position. Call the second one the maximum. Now we need to actually transfer the information. So I don't need this mesh to points anymore. This is just for us to be able to visualize. So I'm going to take our set position and I'm going to pass this through some sample nodes. If you're new to the sample versus the transfer attribute, this is going to be a bit of a weird process. You need 2 nodes to do a single transfer. So sample index and sample nearest. Sample nearest provides us with the index of the nearest point. In a lot of cases, it's much more useful having this as a separate node. I know a lot of the times you're wanting like the nearest position, the nearest attribute. So in those cases, you do need to do a setup like this, where we're setting the position, and then we have this going into the sample index geometry and the sample nearest geometry. We're interested in the nearest points in both of these. And I'm going to be joining up my value, not from this normalized axis. I don't want to know about the normalized axis. I want to know about the original position. So the lowest x, what was the position of its actual position? I'm going to take another position node up here, and I need to capture this position before the set position. Shift A, attribute, capture attribute. We're going to be capturing a vector on here. Apologies if we're going fast. You might need to play this one slower. Let's add a separate XYZ on the capture attribute. And we're just going to be using this as our value to transfer. So we have the original position, the original X position, and it's being transferred according to what the lowest X is, or which X position is closest to the bottom of our curve. So that's how we're doing our transfer. We're storing it based on what is closest to the top and bottom of our curve. That's our minimum maximum. And then we just have that data then to work with. Rather than joining these into 3 different captures up here as floats, we're going to also be combining these into a vector before they get there. So we have this first one done. We can just take these 3 green nodes, Control Shift D, bring them down. I'm going to do a little bit of rerouting at this point as well, just to make sure that things remain somewhat legible. So there we go. This one is going to be our y-axis coming across into the position, and the y-axis from the original position coming into our sample, and join this one up to the y. Same again, Control Shift D, bring it down. This one comes from the z into the position, and the z into the sample index. Make sure that you're not using the normalized index into the samples. This needs to be different between them. Join this last one up to your z, and there we go. Now we've stored the minimum position. Now, why do we have 2 of these? Because technically at this point, we've actually stored both positions. And in fact, we can have a look at this in our spreadsheet. If I look at the control points, we can see that we have our minimum vector per instance and our maximum vector per instance. Great. However, for us to actually transfer this back to the real instances, right now I have 13 instances, but we have 26 control points. I need these to match. So what we're going to do is we're going to delete the end of our curve. But before we do that, we need to store what would have gone to the end point on the start point. And we can do that with a field at index node. So Shift A, utility, field at index. We're going to change this one to vector, plug this one to the value. I want to be doing the index +1. So let's use an add node to add 1 to the index. There we go. So it's basically saying what is the current index +1. That's going to give us the next point along the curve, which will also, for the tops, it will give us the next point, which will be on the next curve. But we're going to be deleting the top points, so that doesn't matter. All that matters is that the bottom of each one is reading what should have gone to the top. This field index is coming off the same combine. There we go. Now we have what should have gone to the top is now also at the bottom. So we have this maximum vector and the minimum vector on the same point. Then we can just do the simple delete. So geometry, delete geometry on here. We're going to be using a curve endpoint selection node with the start size set to 0. So we only want to delete the ends. And this should give us our points. Now we need to transfer this back to the instances because we have all of this information useful. We need to transfer it back. Before we do that, we want to just convert these remaining 13 points into vertices. So we're going to do a curve to mesh. And there we go. All right. So now we have, you can see 13 points. Each one of these points contains bounding box information for its corresponding instance. So all we need to do is just transfer it back to the actual instances. Let's come down here. Let's just frame up. Always important to remain tidy. So I've got this bottom section framed up. I'm going to call this one transform meshes to axis data. There we go. Trying to be descriptive. This section here is our finding the min and the max. Control J, F2, find min and max. I'm just going to turn off my timings here as well. And let's do this final step, which is going to be actually transferring to the instances. So we can grab a group input node up here, and let's get rid of this viewer. So now we've got our instances back. This is what we want. We want to capture on the instances. So we want to be capturing a vector. That's what we're dealing with. We want to be dealing with instance domain. Let's rename this one to min. And let's rename the second one to max. There we go, min and max. And we just need to transfer now from the curve to mesh. So let's drag this off. We're going to be sampling index because we're just going from one point to one point. We're going to be transferring a vector. This first one is going to be transferring the minimum. So let's take our minimum value here and bring it across. The index is going to be just the index. We want each one to go to each other one. So just index to index. This one can plug into our minimum. And there we go. Now we've stored the minimum on our instances. Let's take another one, sample index, Control Shift D. I'm going to cut this vector. Let's actually just connect from the same index to save space. And this time I want to connect from the max across here. And I'll just do some reroutes to keep it tidy. And we want to plug this up into our max capture. On our group output, we want to do a couple of things here. Let's join the minimum and the maximum to our group outputs. Let's rename these ones to min and max. And we want to join our max geometry to the geometry here. Don't need that temporary viewer. Now there is actually one final thing that we might want to do here, and that's to view the bounding boxes. Bounding boxes are a little bit more complicated because we can't actually just calculate the bounding boxes. We need to instance a cube on the correct location for each instance. So let's come in here. I'm just going to Control J on this final section. This was the store on instances. And we're just going to, underneath here, create our own bounding boxes. So let's take our curve to mesh. And we're going to be doing a set position on here. The position that we're going for is the minimum position. So I'm just going to find this. It's the top connection. There we go. So this is the minimum position of all of our boxes. I can now instance on the points a cube. The cube is going to be 1 by 1 by 1. This makes it very easy for us to scale, but it needs to be cornered on the minimum position. So rather than it being centered on 0, we need to add 0.5 to the position of that cube with the transform node. So now you can see it's exactly on the 0, 0, 0 position. Final thing we need to do is to scale these cubes by the difference between these two things. Let's take a vector math, and we're going to be taking the maximum value, subtract the minimum value. This is going to be the scale. And there we go. Let's make sure that we're passing this information out as well. Let's just frame this up to begin with. This one's going to be BB for bounding box. I'm going to plug this one into a new socket on the group output, which I will call bounding boxes. These bounding boxes don't actually have their minimum maximum information. We just want to add this to the captures from here. So we can simply go vector math on our minimum. We're going to just add from the minimum here, which is the original one from our boxes, from our curves, I should say. And equally, we're going to do another one, taking our maximum from the maximum. And there we go. So if you're interested in why this works, like why adding values that exist on one to values that exist on the other, we talked about it a bit in the collection packing tutorial. And essentially, if you have a captured attribute on one object but not another, the other one will just have zeros. So if you add the inverted attribute where you've got values on one but not the first, then you'll basically add to 0. So you will just have it where you expect to have it. So you can always just use vector math add or a float math add or boolean add, whichever it is, to make sure that you've got your values where you need them. Let's just double check that this is all correct. I've just gone into my, gone out here. I've got my instance on points. Let's just check these against our bounding boxes actually. And I'll go into wireframe view, go into the top view and check. All right, these look very close. We can see we've got the boxes as I rotate these, those boxes are nicely conforming to our instances. All right, so the extra step here, we've got bounding box on instances, that's lesson 1. Now we need to do bounding box on rotated instances, which is kind of the same thing as what we're seeing here, but it's just rolling a couple of extra functions in with this and making a new group. The reason for this is that we want to be able to put this actually before the instance packer, just to make sure that we can pack rotated instances. So let's take our bounding box instances. I'm actually going to pull this out, get rid of that bounding box. I'm going to get rid of this random value. And this rotate Euler, I don't need that. This is all just making things stack in a row, which is fine. And we can come back to the beginning. Now I also actually don't need the collection info plus node. Got it marked as an asset, so I'm just going to delete it. It'll stay in the file. I will have my bounding box instances, and I'll mark this one as an asset right now. Let's save. So one of the reasons that it's difficult to do packed rotated instances from a collection, if I do my input collection info here, let's have a look at our objects. The reason is because, for example, in this collection, there's only 4 objects. I have a T-Rex, I have a mouse, I have a backpack, and I have a minecart. If we have these 4 objects, and I'm going to be rotating and scaling randomly, let's say 100 objects, well, I can't calculate all of my bounding boxes based on these 4. What I need to do is I need to instance all of the objects I need with the rotations I need, and then I can calculate bounding boxes on them. From there, I can then repack them. So that's what we're going to do. We're going to take our collection info. We're going to instance on points, and we're going to be using a points node like this. We're just going to instance them all in the same position. It doesn't matter. Our bounding boxes are going to be per instance. It's not going to complain that they overlap. And our next section, where we do our instance packing, is going to repack everything anyway. So we don't need to do any positional stuff. What I want to do is I'm going to take these 4 nodes, actually without the collection info. I'm going to keep that on the outside, because you don't always want to be using a collection. Sometimes you've made objects inside geometry nodes. You've done something like a geometry to instance, or you've just instanced them. We want to make sure that this is still a general tool. So collection info on the outside. Take your points, instance on points, and bounding box instances node, Control G. I've got my instance coming through here. I'll make that plural. I'm going to plug in a count, which will go at the top. So this is just however many we need. And then I'm going to make sure that I've got a few extra connections coming in here. So pick instances is going to be on because we're dealing with instances here. Would we ever want it to be off? Let's go ahead and connect it just in case somebody wants it off. We're going to deal with our instance index as well. We're also going to deal with our rotation, and we're going to deal with our scale here. So might as well do it all, seeing as we're instancing everything anyway. Just let's do the calculation here. After the instances, we're going to just put on our bounding box instances, and our group output will take instances. It's going to take the min, the max. Might as well take the bounding boxes as well. And let's take our group input to the front here, and let's just plug in our count, just so that we have it controlled from one place. Just noticed bounding box instances. Let's go ahead and just change the output node on here to instances. It's always good practice just to be descriptive about the information you've got coming through. And the input as well should be instances here. There we go. So that's sorted. A little bit of housekeeping. Let's tab back out here. I'm going to rename this one to bounding box instances rotated. So just adding a word there. I'm going to mark this as an asset while we're here. The rotation I will leave exposed. The scale I might as well leave exposed as well. I don't mind having big nodes. You can always hide these values. One thing that we're going to need to deal with though is the instance index. Now, if you were with us in the previous tutorial about the collection packing, you'll know that we did a weird little janky thing for the instance index on that one. And we're going to just do the same here. So you can see I made a whole list of these, right? And if I actually just remove from the instance index, you can see that we have all of these different objects. So what's going on? Well, the instance index from the group input is just reading 0. Whereas if we're unplugged, it's going to be calculating this based on the index instead. So if we want to be able to control the instance index, we need to be able to plug into it. But if we plug into it, we need to make sure that when we're not plugging into it, it will keep using the original index. We can do this in a pretty horrible way. So let's unhide the value so that we can come onto the front here. I'm going to set this to minus 90,000. That's just the value we used in the previous tutorial. We're going to copy this value. And the reason I've used a negative value that's very large is because it's unlikely that you're ever going to use this in a real situation, this value. You're almost always going to have positive integers, and 90,000 as well. It's just a very big number. So it's unlikely you're going to hit this. And so that's basically safeguarding that collision. If I come back in, I'm also going to make sure that this is the default value on this socket. If I use a compare node and I find out where this value is equal to that minus 90,000, now I know that when nothing is plugged in, it's going to be minus 90,000. So this will be true when I want to use the index. Let's use a switch node. Plug this into the switch. I'm going to be switching between integers. So when it is true, there's nothing plugged in, and we want to use the index value. When it is false, that means that something has been plugged in, and at this point we want to use that socket. So let's plug this one into our instance index now. We can see that we are still using the index. Everything is still different. So there we go. I can move this. Let's just frame this one up. Call this one instance index default. There we go. All right. This is the whole node group for our rotated instances. Go ahead and save. Let's just double check all of this works. So we can take our instance index no longer needs to come from this instance packer. We want this we want this on our rotated version. This one's going to be dealing with instancing all of our things. So we want to deal with it early. Flip instances, this can probably stay here, I think, and the scale, it could either go here or we can come onto the rotated instances. It doesn't actually matter. I'm going to plug it on here because we might as well. We're going to deal with rotation, but first of all, let's just plug this through. So instances comes onto our instance packer, min into min, max into max. That's all good. And these instances also get instanced directly over here. All right, so far so good. Looks like we would expect from something that has 0 rotation. What happens when we start rotating? So in theory, as we rotate this, there we go, we can see that this is starting to pack down. You will notice that there are gaps between things. This is because what we're doing is not a solved pack. We're not doing physics, we're not looping, we're not checking for collisions. What we're doing is we're basing this strictly on the bounding boxes. So you will get a fairly close pack, and it's going to be a lot better than just doing trigonometry based on the bounding boxes. We're able to actually compute this. So for randomly shaped objects like the mouse, it's going to deal much better than if you were just doing it based on the bounding box. All right, that's looking pretty great. So far we have done bounding box instances and bounding box instances rotated. We have one more thing we want to make in today's session, and this is bounding boxes for group indices. And this is actually just a generalized version of the bounding box instance version. Hopefully this is making sense. It's all of the same maths, it's all of the same calculations going on. We just have to do a little bit more when it comes to transferring it back because we're going to meshes. So let's see how to do this. First of all, I'm going to make a new object. Let's use a grid object, mesh primitive grid. Let's view this. I'm also just going to grab an input position node. I need to make some group indices here. So let's take our position. Let's do a separate XYZ. And if I just view these two together, this is what we see. Let's increase our vertices counts here. Let's go up to 100. And what we also want to do is just as we did before, let's go ahead and do a attribute statistic. This time onto our X value. We're going to be doing a map range from this X value, the original, and we're going to be using the statistics here just to group everything together. So now we've got 0 to 1 value, which we can see here. Regardless of how big this goes, it's always going to be 0 to 1. A little bit more fun than this, we can actually set this from linear to linear stepped. This is going to give us steps, and we have 4 steps, so let's go from 0 to 4. The step is actually in between the things, so if you have a 0 and a 1, that is 1 step. So 4 steps is going to go 0 to 1 to 2 to 3 to 4. Even though you have 5 indices, I've never really understood that one, but now if I have a look at my spreadsheet, see I've got 0s and then 1s, 2s, 3s, 4s coming through my viewer. So these are going to be our group indices. Obviously, on a real mesh, on a real example, you would have something a bit more interesting. For the sake of demonstration, I'm just going to be dealing with this plane and working out bounding boxes per group section. We can test it on a different mesh later. Let's bring in our group bounding box instances. And this one, we're going to click on this little 2 to make it a new node. Just because we're going to be making changes, make sure you've changed it to a new node. Otherwise, you're going to be overwriting the original. So this one's going to be bounding box group index. Make sure you're saving this one as an asset, and we will just plug this into our object here. Now, we're not dealing with the instances anymore. So let's come in, let's rename our sockets to geometry, because we can deal with both meshes and point clouds. So let's go geometry on the outside as well. And we keep everything else. Min, max, bounding boxes, that's going to be useful information. So some things I can get rid of. This store on instances, that's got to go. We are going to be doing the exact same transform meshes to axis data. However, in this one, we don't need the realize instances because no instances. So let's get rid of that, Control X. So this transform meshes, that's fine. We're still going to be using this multiply by 500 to deal with our offsetting in the x-axis. Again, that's fine. We don't need to capture the attribute on our geometry, because in this case, we're actually assuming that the information already exists and we're already in a mesh state or a point state, so that information is going to be accessible. So at this point, I can also get rid of the capture attribute and index node, get rid of this. We need to add a new socket onto our group input. So just add up here. We want to be adding an integer, call this one group index. And I'm just going to hide the value for neatness, seeing as you only ever really need to plug stuff into it. Let's just go ahead and grab this group index into our multiply. And that's actually most of what we need to do. The storage, this needs a little bit of work. This process is fairly straightforward. So we can take our group input, let's plug onto here with our Shift Alt left click. And from here, I want to make sure that I only have, if I view this with a viewer, and I plug in my index to the outside there, I need to make sure that I have as many points as I have group indices. Right now I should have 5 and I've only got 1 mesh. So when I do my instancing, if I was to just use the points of my mesh, I would have 10,000 curves. That's much too many. I need 5. So what we can do is we can use the fact that this is geometry to actually do some of our data wrangling. I'm going to get rid of this instance to points node. We don't need this. I'm going to be taking our geometry through a set position, and we're going to be positioning it on our multiply by 5 group index, right? This is our offset positions. So if I view this, and it's not going to show up very clearly just because it's all in a line. So let's go and just for the sake of visualization, let's also use a mesh to points node, just so we can see. There we go. So we do still have 10,000, but they're all on 0, 5, 10, 15, or 20. So this is geometry. We can merge by distance. It's pretty simple and it's going to work. So Shift A, geometry, merge by distance. As soon as I put this on here, we're down to 5 points, which is great. We don't need any more than 5. We only need 5 specifically. So we have our set position, our merge by distance. This creates the points that we want, which can go into our instance on points node. And then the realize instances is going to create us 5 splines where we need them. Let's just put this over into our storage. So it's one step extra, but it works for geometry. All of our transforming, this is all dealing with point domain anyway, so this is going to work. All of our find min and max, again, it's all still going to work. This is all consistent logic. The bounding boxes, even the bounding boxes are going to work. In fact, you can see that these are working fine. We do have gaps. The gaps are caused by the fact that we're dealing with point indices. So there's going to be a face that is emitted in between two rows of points where you have one integer and then the next integer. If you wanted this to be based on face corners, then you're going to be specifically limiting yourself to meshes, which might be fine. It might be what you need. The way that you would do this is you would essentially capture, let's just do it, attribute, capture attribute. You would capture your index as an integer on the faces instead. So now if I view this, you can see that we have a sharp edge between our different indices. And from here, you've got your set position, which is actually, you would probably want to do a mesh to points, and let's set this to faces. And you could potentially just use this as the vector into the position, but the idea is anyway that you've got your 5 points you can merge, and that's then done. If we view our bounding boxes now, then you can see that they join up because we're dealing with face corners. Face corners, obviously faces join at edges, so that's a lot more kind of consistent, but you are limiting yourself to meshes. You couldn't plug through a curve, you couldn't plug through points. Just for the sake of making this more flexible, I'm going to keep this using just the points. I think it's fine. I've never run into an issue where I've needed something else anyway. So for me, this works. So group index, that's all we need. Moving across to the end, we do need to find out how to actually move this back to the mesh information. It's still fairly straightforward, but it's a little bit more of the same idea where we position stuff onto a known value, transfer by nearest, and then we reposition back to our original geometry. Let's grab a group input node at the beginning here. Here we go. I'm going to be capturing on here the vector of the position. So this is the current position for each point. I am then going to be using a geometry set position node. And I'm going to be positioning this on the group indices, and not just the group indices directly. I want to do the same thing we did before with the multiply by 5 in the x-axis, just to make sure that everything is in exactly the same positions. So there we go. It's all disappeared just because of things sort of flattening down. Blender doesn't draw faces well when they're flat. So just for the sake of demonstration, I'm going to put this on like this. So now we can see all of the mesh is compacted down to the points on which we've actually stored all of this information before. Much the same now, we're going to be just capturing. So attribute, capture attribute. We're dealing with a vector on the point domain. Make sure you've got this set to point. Let's rename this one to min, duplicate, rename this one to max. So I've got my min and my max capture attributes here. I need to now transfer from these, which are our sort of our memory. So let's go ahead and we're going to be doing a sample index. So let's join these up. Sample index. We're going to be sampling a vector attribute. Let's just move this all up on the point domain. And the attribute is going to be the minimum, which can come up to our minimum version. And I want another one, which is going to do our maximum into our maximum capture. We don't actually have information about which the nearest point is yet. So let's also use a sample nearest node. And this time we're going to be using the same, so curve to mesh. And this is actually all we need to do. So each of these points is going to evaluate at the capture which of the points in here is closest. Because we have a 5 meter spacing, there's going to be no doubt as to which that is. So we can just join in our indices now like this. All right. Move this one up. And there we have it. This should be really all of the computation we need to do. Control J on here. This one is going to be store on mesh. And actually, before we move on, we do need to reposition our points. If I have a look at these, we just have these points going off into space. Let's Shift A, geometry, set position. We are interested in the original captured position. And now we go back to our plane. So that's why we capture before, because we need to transfer to our memory position, transfer everything across, and then we can reposition our geometry. We're not doing any deletes. We're not changing index order. We're not doing anything. We're just screwing it up to where we need the information and then unfolding it again. It's a nice, easy process. Still actually fairly quick, and yeah, just makes everything possible. So there we go, set position joins into our geometry output. I'm going to be plugging my minimum and my maximum into these two add nodes. Make sure you get them the right way around, just so that we have the bounding box information and the information on the mesh. So tap back out. If I look at my viewer, I can now see this is my minimum bounding box position, or my maximum I should say, and my minimum version is here as well. So rather than working on our grid now, let's use something a bit more interesting. Let's grab a Suzanne. Let's make sure that we're plugging into our bounding box index and our attribute statistic node. And what I can do is I can just check this is going to work. So we've got our minimum and our maximum, that's all right. We've got our steps coming across here. And we've got our geometry, that looks fine. So this is our min and our max values. Let's have a look at just the bounding boxes. How cool is that? All right, so this is the literal bounding boxes of Suzanne when stepped into 4 horizontal sections. Let's make that a little bit higher subdivision. There we go, that's cool. Maybe we can try something a bit different. Rather than using all of this math stuff, let's just throw in a texture, Voronoi texture. Let's have a look at what this looks like. We've got our color. Let's just use a math node, multiply by 500, something like that. Just should give us enough like differentiation between different points. All right, that looks awesome. So let's just make sure that we're logically working through this. If we come in here into our storage, because we're setting position just onto the points and that we are merging by distance, it means that if I just demonstrate this with a mesh to points node, there's going to be some points, they're miles away. So you don't need consecutive values in your group index. It doesn't matter what you use, the system is going to make it consistent. So that's awesome. So now you can do bounding boxes for any arbitrary piece of your mesh or instances. You can do rotated instances packed along a spline. You can do anything. If you're interested in these more technical things where it's more like making tools, building more complicated systems rather than like a simple exercise, let me know down in the comments because it's really useful to know how people are gauging this stuff. So hope you've had fun. Hope you've learned something, and I'll catch you in the next one. Hopefully this is making sense.